So the specific thing that we are looking at is actually what I would call as transactive control. How do you combine the active control concepts that have to be implemented in a power grid, like making sure that the frequency stays constant and that the power is delivered, along with the market transactions, which basically determine the pricing strategies for different components, and how that higher level decision making is synergistically managed along with the lower level decision making of how do you control these different units as to how many megawatts of power they need to deliver, and how do you make sure that the frequency is regulated. And all of these things happen simultaneously. So this market transactions plus active control have to be tightly integrated, and we're looking at that integration and how that should happen. And this might mean that there's a different way in which markets have to function, especially in the context, I mean, I'm really talking about electricity markets. So there needs to be perhaps some dynamic market mechanisms that essentially carry out these decisions. So we're looking into that. There's this concept called adaptive posicast control. And what it is basically that it allows you to collect the information about the specific automotive system, and it positively forecasts what it's going to do certain seconds in the future, and use that information in order to design how, let's say, the throttle position has to be changed, or how the air-fuel ratio has to be changed. And so this is a fundamental concept that tells you how complex dynamic systems should behave, and it translates into something very tangible in the context of this powertrain for, you know, for the automobile. So here is I think a perfect example of how engineering science should proceed, where, you know, you develop these fundamental concepts, and this is the size and shape that this concept takes, and it actually can be translated into X% improvement in performance, and therefore Y number of dollars of savings in, you know, per automobile. And those X and Y numbers were actually sufficiently compelling for, you know, to take that concept and explore that further. And it's been more or less the same kind of thing with Boeing as well. So we wrote a paper where we explored a particular historical event that took place in 1967. And what happened was that this is a high-performance aircraft. And they said, okay, I'm going to introduce certain adaptive concepts. And this, by adaptive, what they meant was that certain gains in the loop were changing. So these, this adaptive concept was then implemented, and they had highly successful flights, except one of them basically led to a series of events that were unfortunate and culminated with the accident, and they lost the aircraft and the pilot actually. So we explored that historical event, and we were able to analyze it as to what happened. And so it's a what scenario. And also we played a what if scenario, which is that, okay, suppose we were to take away that adaptive concept that they had in that vehicle, which, by the way, was, you know, way back in the 60s, before we really understood how to design adaptive controllers. So we took that and we replaced that adaptive component that they had with what we know now as to how, you know, how adaptive controllers should be developed. So we replaced that technology. And then we recreated the whole vehicle, and then we said, look, if you switch out their stuff with what we have developed, here is how that aircraft would have performed. And whereas if you had what they'd had, we can predict that this crash would occur. So we provided that comparison, and that basically led to a very clear understanding of how adaptive flight controllers should be developed, and we got a Best Paper award for that. So here is a case where, you know, where we worked with my Boeing counterpart, and we had the successful collaboration that led to a satisfactory exploration of a fundamental concept in the context of the flight vehicle.